today's lesson, we are actually going to be calculating mean and standard deviation and talking about what that actually means within a proportion. So yesterday we learned how to check just a few conditions with a sample size to make sure that we can assume it has that normal bell curve. And so we checked sample size, we made sure it was random, and we checked that we had enough successes and failures within our sample. So today we're actually going to calculate mean and standard deviation only if those conditions are met. So that's why I picked examples from yesterday that we already know if the conditions are met, we don't have to go back and redo those. So the mean of a sampling distribution whenever you're working with proportions is just the probability of success. So the mean, we use the notation, that is a Greek letter mu for the mean, and that's the probability of success. And then to find the standard deviation, that is a lowercase sigma, another Greek letter. And we take the square root of the numerator is the probability of success times the probability of failure, and we divide that by the sample size. And you guys will use your calculators for this, so make sure you have your calculators out because you are going to need that square root button today. And we're also going to do, we might do a little bit of work with the calculators, but the calculators are tomorrow's lesson. So you guys will have a short video to watch some calculator instructions. I've already posted the Khan Academy video that goes with it, but it's only one example and I felt like it wasn't enough. So I will be, during 6th hour after school today, recording a few examples for you guys to watch to help you with your assignment tomorrow, since you guys won't be here. All right, so these are the same values as yesterday. P is still the probability of success. Q is still the probability of a failure. And then the value of N is our sample size. And I drew that bell curve for you just to remind you that the mean always goes in the middle. And then our values across the bottom always increase by a standard deviation at a time. So whatever that standard deviation is, we add it to complete the right hand side, we subtract it to complete the left hand side. I'm going to say these are things that we did in like September, October-ish. But I want to, before we go through these examples, I want you to know that sometimes you're going to see just a P by itself, and sometimes you're going to see a P, which we call that a little hat. We actually just say P hat. Whenever someone is referring to a proportion or a probability from a sample, they're always going to denote that with P hat. That is an observed thing that actually happens, but for our formula, we actually use the expected proportion for the entire population. So if you're given two proportions or two probabilities, always make sure when you're plugging it into the formula, you're doing the one that goes with the population and not the sample size. And we actually won't get to that even until example 4. So the first 3 examples, we won't even have to worry about that. All right, now, and you might have to, the first 3 examples, you will need to refer to your notes from yesterday to figure out where those numbers are going. What's that? Let's see if I can zoom in one more. There we go. All right, I think that's good. All right, so yesterday, the ghost example. What was the probability of success of someone believing in a ghost? Hold on, gotta look. 0.45. All right, 0.45. So if the probability of success is 0.45, what's the probability of a failure? All right, and don't we always get that from 1 whatever the probability of success is, subtract it from 1, and that's going to give you your Q. Now, yesterday on that ghost example, what was the sample size? 808. All right, so it tells us here that the mean is always the probability of success. So if the probability of success is 0.45, what's the mean? It's the same. All right, the mean is 0.45. Now the standard deviation, we do have a formula. Inside the square root, the numerator is P times Q. So we're going to take 0.45 times 0.55, and then we're going to divide it by the sample size. So this is where you're going to need your calculators. So in your calculator, you don't have to worry about parentheses. It knows order of operations. So when you type this in, you simply just type in the square root, and then you are going to take 0.45 times 0.55 divided by 808, and it gives you the standard deviation. And we're going to round to, let's go nearest thousandth. So if we divide that, what do we get? And we're going to go near thousandth, so 0.018. And if you write 0.0175, I'm not going to be picky on your rounding. Thousandths or 10,000ths is close. They're not going to make dramatic changes to an answer. All right, so your assignment on Khan Academy today is specifically calculating mean and standard deviation, and that is it. The mean will be given to you. The standard deviation you'll have to calculate. Now, I do want to show you guys what this means because you're going to be working with curves a lot tomorrow, so I wanted to make sure that you guys are okay with setting up the curve. So the mean always goes in the middle, and then each increment on our line is going to go up by a standard deviation. So every single time we're going to add 0.018. So my first is 0.468, then add 0.018 again, and I get 0.486, and then add it again, and I get 0.504. All right, how many of you guys remember doing this earlier in the year? So whenever we're calculating probabilities, we have to make the graph. So that's why I want to make sure you guys are comfortable with that. So then we have to also go on the left-hand side. So we're going to take 0.45 this time. We're going to subtract the standard deviation each time. All right, now once you have that curve, because we did calculate yesterday that this met the normal conditions, so we were good to go. So now we can describe a few things that are happening without using the calculator. So see if anybody remembers. Does anybody remember the percentage of data that is included from -1 to +1 standard deviation? You guys remember what percent goes here? 60, 68. So 68% of the data goes in between -1 and +1. Now, what about from -2 to +2? You guys remember the percentage there? Close. 95. All right. over a couple Post-its. Yes. 99.7. And you might see some textbooks say 99.5. But what this is telling us here is the majority of the data, like almost the entire data set, is going to fall in between 39.6% and 50.4%. So if you were to do this same survey asking people if they believe in ghosts, if their claim is true, and you did this study and it was truly random, 99.7% of the time your results of people that would believe in ghosts would be in between this and this. Now, 68% of the time you're going to expect this. 95% of the time, and then obviously your ability of being more accurate is going, the farther you kind of spread out your range, the more accurate it's going to be. So this is what I just wanted you guys to know. If you were to describe this, I probably should keep this color coded. 68% of the data is going to be in between 0.432 and 0.468. Now, your Khan Academy assignment's not going to have you describe, but I promise you the AP test will have you describe some things here. Then our second set, 95% of the data would then be between 0.414 and 0.486. And then your final one, 99.7% of the data is in between 0.396 and 0.504. Now, if you had something like with a result of like 0.55, what that means is you probably made a mistake somewhere, or it's just an outlier, one or the other. And then you would have to make that assumption to do something like that. You'll say, it's not too bad today, is it? You'll say, the curves are just a review, just to make sure that you're prepared to make the curves for tomorrow, because we will be doing some probability. But I wanted to make sure that you guys could see that, and I am going to zoom in on this speed trap question a little bit more, because it's writing pretty small. All right, so I am zoomed in. All right, so we're going to do the exact same thing with the question from yesterday, talking about the state police and the speed trap. Jacob, do you have that? Dawson, do you have that example from yesterday?
Yep.
All right.
Right here in front of me.
All right, so what was the probability of success? How many people do they say speed? You gotta find it.
Yep.
All right.
You want like the number or?
I want the decimal.
Yeah.
So if it's 70%, what's the probability?
Oh, 0.7.
There we go.
Sorry.
All right, no, probability, that's one thing. All of our answers are going to be in decimals because we're dealing with proportions. So this one is 70%. What's my probability of a failure then? 0.3. And how many cars did they assess yesterday? 80. All right, so the mean is always the probability of success. So what's our mean here? 0.7. Now, standard deviation, you're going to have to do some work. All right, what do I put in the numerator? It's P times Q.
0.7 times 0.3.
And my denominator? Yep, let's plug that in. The square root of 0.7 times 0.3 divided by 80.
.051.
I think that sounds good. 0.051. All right, this one's not going to work. All right, make or miss.
Oh, if if you miss it, I'm saying make, if you miss it.
It can't be any worse than you last night, right?
I didn't make one though. There you go.
All right, it's good.
I'm done.
Jacob, I'm sorry. You know I'm
No,
just kidding,
no,
right?
don't apologize to me. Don't apologize to me.
All right, I gotta find a green marker that works. Okay. All right, so whenever we build this curve, what are we putting in the middle?
The me.
All right, so what number is that?
0.7.
All right, 0.7 goes in the middle. So then every single standard deviation, we're going to add 0.051 to the right. We're going to subtract 0.051 to the left. All right, 0.751. 0.802. 0.853. All right, you guys all agree with those numbers?
Yep.
All right, now let's go the other direction. So we're going to start with 0.7 and subtract 0.051. So we've got 0.649, 0.598, 0.547. All right, so for this one, what values do we use for our 68%? We expect them to be from, what's the lower number and what's the higher number?
649 to 0.75.
Yep. All right, then the second set,
598 to 0.802.
and the last one,
547 to 0.8.
all right, 0.547 to 0.853, and what's the percentage there?
99.7.
Yep. All right, so what this is telling us is that if you were to set up a speed trap anywhere, 68% of the time, you are going to find speeders, or the amount of speeders is going to be between 64.9% and 75.1%. We expect 70, so that first standard deviation, the range is a little bit closer to 70. Now, 95% of the time, our speeding percentage is going to be between 59.8 and 80.2. Again, as the percentage increases, so does the range. And then 99.7% of the time, your speeding percentage is going to be between 54.7 and 85.3. So do you guys have any questions on these first two? All right, now, I want you guys to go back to the M&M's question from yesterday. Because, correct me if I'm wrong, the M&M's question yesterday was not normal. Was that right? Because were we short on successes or failures? I honestly don't remember. Okay, our successes were short on the M&M's question yesterday. I think it was like, what was it, 10% of 50? So we only had 5 successes in the sample, and that wasn't enough. We needed 10. So the first thing I want to ask you, yesterday we sampled M&Ms that were in bags of 50. What if we sampled them in bags of 200? Do you think that would help? just having more samples.
Yeah.
So, would this still be random?
Yeah.
Okay, so it's still random, so that's good. Now, the 10% rule. Would 200 divided by 10% still be less than or equal to all M&Ms?
Yeah.
All right, we can assume that there's more than 2,000 M&Ms in the world. And I say I got to make sure my camera's in the right spot. All right. So then the last part, we have to assume that we have 10 successes and 10 failures. Now on this one, what was the probability of success? Was it 0.1?
Yeah.
All right, so now we have a sample size of 200. Our success is 0.1 and our failures is 0.9. So really you only have to check the smaller one, because if the smaller one works, so is the bigger percentage. So what is 200 times 0.1? All right, so we have 20 successes, which means that you take 200 times 0.9, that gives you 180 failures. So that works too. So all three things work. So this is now normal. Just increasing the sample size made it a better sample. So yes, it is normal. Or at least, we need to make sure that we're saying approximately normal. It's not perfectly symmetric, but it's close enough. And that little squiggly does mean approximate. So once we know that the normal conditions are met, now we can calculate the mean and standard deviation. So the mean's the probability of success, so what's our mean? Point 0.1 or 0.10. All right, then our standard deviation, we're going to take P times Q and divide it by our sample size, which is now 200. All right, so I'll give you guys some time to plug that in. I saw numbers when I came in for a minute.
No,
All right, so our standard deviation. Annalie, what did you get?
0.0.
Do you guys agree with that? All right, so I'm going to give you guys some time to build the curve and then answer the questions about the 68, the 95, and the 99.7. Now say, let's go ahead and get that done on your own. And I don't think it matters how many times I do this lesson. My bell curves never look good. They continually. Is anybody good at drawing these curves yet, or is it still like a little lopsided? Mine are usually just a little lopsided. That one's
but
great.
the rest of them are not. One turned out really, really good.
All right, Chloe, do you have the numbers to go label that?
Yeah.
Will you go label that curve? Pick a color, just not black. you've got 0.1 in the middle, and then going to the right, what are those values? 0.121, 0.142, and 0.163. And then going backwards, 0.079, 0.058, and 0.037. All right, now, do you guys think that you could write these statements yourself? About 68%, what values would, so what values are the 68% range? All right, 0.079, 0.121, what's the 95% range? Yep, and the 99.7% range? All right, I think that sounds good. So, we do have one more example and then just a little afterthought about sample sizes. So I'm going to give you guys some time to write down this example. Now, if you can see, this is, a lot of them, the problems are straightforward. They give you the probability of success. Here we have two percentages and we have to decide which one to use. So I will give you guys some time to write that down. I'm going to get my cameras organized and get something to drink because I'm talking too much today. Oh, and I wanted to let you guys know, Carly informed me that I was super rude yesterday and I did not introduce the person sitting in the back of the room. After school, she was like, who was back there? So that was my fault. That is Mrs. Cooney, and she is going to be short-term student teaching here. She's actually...
Is that like Mrs. Cooney, like related to Senor Cooney, or?
Yes.
in life?
Mm-hmm. So she is student teaching, and she will be within the math department. She just wanted to come and watch stats. She will not be teaching this class, but she was just observing yesterday, and so she just decided, since she'd already sat through geometry with Mr. Boyd a couple times, she thought she'd just change it up for the day and come in and listen to stats for a little bit. But she will be here until what day? Through spring break. It was supposed to be March and April, but she has been approved by ISU to complete her stuff at spring break. So when she comes back from spring break, she's actually going to be Mrs. Unger at Carlisle for the rest of the year. So
Where's Miss Unger going?
she's having another baby. So she, yeah, lots of student teachers right now, which is a good thing. But I just wanted you guys to know, if you see Mrs. Cooney downstairs, like, she is a student teacher. She always wears she has her ISU badge. Just be welcoming, because it's intimidating whenever you go into a brand new school. And with her teaching experience with COVID restrictions, it's been very different because she has not been in the schools like most education majors have been. So this is like, honestly, like right now is like the first time in a long time that she's been in a school setting. So she was with Mrs. Shake from January until last Friday. So she was with Mrs. Shake for a little bit, and then she's here, and then she's going to be at Carlisle. So all right. So on this one, it says, suppose 35% of students in the U.S. sing the national anthem correctly. How many of you think that you're in that 35% that you could sing it correctly?
Like lyrics or pitches?
Don't ask me to sing.
Oh, no. Pitches, no. Lyrics. How many of you guys think that you know the words of the national
I
anthem
know
without
I can sing
help?
it better than Fergie did, though. That's for sure.
Have you guys seen the most recent video of the lady who sang it for like some sort of convention, and she changed keys 9 times while she sang it, like on accident? Like she was just like all over the place. It was it was so bad. It was almost worse than Fergie. I don't know if anybody has seen it.
That would probably be less than I would.
There was
I
I feel
cannot
like even if
sing.
it's not
There
good,
was a
you can say
comedian
it's-
lady that sang it before a baseball game once, and it was terrible. She just pretty much talked. She pretty much said the lyrics into the mic, and it was deep
That's
chord.
so, like,
Okay.
it'd just be so awkward.
All right, so let's say that. So, it is expected that 35% of the students can sing it correctly. Mr. Samarja decides he's going to take his own random sample of 30 students, and he finds out that 40% could sing correctly. We want to know if this is normal. So,
Wouldn't we take the 35%?
okay. So, let's talk about this for a second. One of them is a P and one of them is a P hat. Okay. So, P hat is the one that we observed from the sample. So, which one is the P hat? The 35 or the 40? All right. The 40 is the P hat. The 35% is the assumption for the whole population, right? That is the P value, not. Now, which one did I say to use in the formula? We use the population. We use the overall proportion for the formula. So, I wanted to make sure that you know, even though it says find it for P hat, the formula still says to use the overall proportion. So on this one, we are going to use 0.35, and we're still going to use P and Q from this. So we are going, my P value is 0.35, so what's my Q value? 165. Now my sample size is 30. So you still use the sample size. So the formula always deals with the entire population. So then you guys can plug this in. Let's see, 0.35 times 0.65 divided by 30. You guys get 0.087? Yep. Now, do you guys think you could set up a curve and tell me the percentages? We're not going to do that for this one. But I wanted to make sure that you knew you don't use the proportion from the observation, you use the one that's the overall. So always use the overall population. Now, this is my last thought for the day. What happens if you increase the sample size? If I increase the sample size, will that change the mean? Well, the sample size is which variable? P, Q, or N? N. Does N have anything to do with the mean? Nope. So if you change the sample size, the mean will stay the same. Now, what do you think happens to the standard deviation? You think it goes up or goes down? And here's a really quick way that you can do this. All right, so let's just use that last example. So when the sample size was 30, we got a standard deviation of 0.087. What if we change that sample size to 300? Plug that in. What do we get for the standard deviation if we change the sample size from 30 to 300? So if you change the sample size, what does the new standard deviation become?
0.028.
All right, so when I increase the sample size, did this get larger or smaller compared to the last? Much, much smaller. So So if you increase the sample size, it is going to shorten that standard deviation down. So, and just think about this. Would you trust, do you think having more samples would get a more accurate answer? You know, say the more things you try something, the more accurate it becomes. Because the first few times it might be all over the place, but then over time, and I always like to talk about that with grades. At the beginning of the 9 weeks, every time you enter in a grade, like it really goes up or like, you know, if you put a 0 in the first week of the 9 weeks, it tanks your grade. Does putting in a 0 at the end of the 9 weeks, if there's 1,000 points, does it really affect your grade as much? No. So, like on that one, the more grades you get, the less variation you have in your grade. The fewer grades you have, the more variation each grade has. So you guys do have an assignment today. I don't even remember how many questions it is.